Good morning. In today's lesson, we're going to look at what I call reverse Riemann sums. It's not really reverse Riemann sums, it's just Riemann sums and how they're related to definite integrals. And so we're going to start by reviewing Riemann sums, like how to find a sum, which means you're approximating the area of a region with rectangles. So we're going to find the area of the region that's bounded by f of x equals e to the x equals 1, x equals 3, and the x-axis using a right Riemann sum with 4 equal subdivisions. All right, so I always think it's best if you start with a picture of the graph. Okay, so e to the x is a standard graph you should be familiar with. All right, and you should know that it crosses the y-axis at 1, and it actually never crosses the x-axis, right? But that's a y value. It says this one is bounded by that graph x equals 1, so we'll put that here. X equals 3, I'm just kind of spreading things out, and the x-axis, okay? So I'm talking about this region here, okay? Now, because I'm using a right Riemann sum with 4 equal subdivisions, I basically need to divide this area here into 4 equal, or like along my x-axis here, I need to divide this up equally so I can create 4 rectangles. Now that, so you can like put marks in here to divide it up as equally as you possibly can. And you can typically figure out that if I have to go from from 1 to 3, the middle is going to be 2, and then what's halfway between 1 and 2, that's going to be 3 halves. What's halfway between 2 and 3, that's going to be 5 halves. But there actually is a formal way of finding that. All right, we call that delta x. So that's actually going to be the width of our rectangles, and there's a formula, b minus a over n. Remember, a and b are the intervals, so this is a, and this is b. Whoop, that's really bad. But the beginning and the end of the interval are a and b. Okay, and so in this case, we would do 3 minus 1 divided by 4, because n is the number of rectangles. We get 2/4, which is 1/2. And again, that is our width. Okay, that's going to be the width of each of our rectangles. Now, when I actually draw my rectangle, I have to touch the curve, okay? And then it specifically says using right Riemann sums. And so when I look at this first rectangle, it's the right side of the rectangle that determines my height, okay? And then when I get to the second rectangle, it's the right side that determines the height, and so on. All right, so my rectangles, so actually I end up needing to go all the way to the end here for my last rectangle, okay? And then remember to find, so like we're doing area of a rectangle, which is length times width. Area equals length times width, where the length is literally the function evaluated at each value of x that I need to use. So the right side of each rectangle, it's the function evaluated at that right side of the rectangle. All right, so if I were going to actually write out my area, okay, for each individual rectangle, for the first one, I would do the length times width. Well, the width is going to be 1/2 for all of them. And then the length is going to be literally the function evaluated at the right x value. And then the second rectangle is going to be the same width times the function evaluated at the next right side. And the third one is going to be evaluated at the next. And the fourth one is going to be evaluated at the last right side. Okay, well, to find the area, I need to add up all of those things. You can see that they all have a 1/2 in common, so I can certainly factor that out. but then I actually need to plug 3/2, 2, 5/2, and 3 into my function, which was e to the x. So we're going to get e to the 3/2 plus e to the second plus e to the 5/2 plus e to the third, okay? And at this point, you know, I don't really care what the final answer is for that, but because you would have to type that into your calculator, okay? Well, with Riemann sums, because you're adding up a lot of things, instead of writing it out, all the terms, you can actually use summation notation, okay? And summation notation is something that you learned a little bit about in Algebra 2, all right? So what I'm saying is we want to take the sum, okay, and the variable here doesn't really matter as long as it's not n, because n is going to be the number of rectangles, all right? So you can do k here or I, those are the two common ones. You start with from one rectangle all the way up to n, all right? And then you need your function evaluated at some x value that represents which rectangle you're on. So that's, we call that x sub k. And then you have to multiply by the width. But you do have to understand that the width is found by doing b minus a over n, all right? And your x sub k is really going to be found by taking the starting a value, which in this case would have been 1, and adding that change in x, that width, times whichever rectangle you're on, okay? And so like I would start at 1, but I would have to add my width of 1/2 for the first rectangle. Or I could start at 1 and add my width of 1/2 for 2 rectangles and get myself to the 2. So that's where that formula comes from. So if we take that information, all right, and we say, okay, well, if a equals 1, because I'm going back to this problem, and delta x equals 1/2, then x sub k for this problem would equal 1 plus 1/2 k. All right, and so the Riemann sum, the Riemann sum for this problem, so the Riemann sum for this problem would be the sum from k equals 1 to 4, because we're doing 4 rectangles. Our delta x, a lot of times that will go in front, and then times our function, where we're using 1 plus 1/2 k to find the value that we're going to plug into our function, okay? Now, remember, our function was e to the x. Whoop, sorry, wrong way to write it. Our function was e to the x. So I can actually write this even more simplified by actually plugging this 1 plus 1/2 k into my function in place of x. And that is an official Riemann sum, okay? Now, the way I wrote it up here, this is where we have n subintervals, and then in our case, we knew that we had 4. All right, so like you have to remember, like, how do you make, so because technically this area that we found is just an approximation, right? And in our case, it would actually be an over approximation. And so you have to remember, when we learned Riemann sums, we talked about how do you make that approximation more accurate? And you make it more accurate by using more and more rectangles, right? And so if, let me start a new page. All right, so if we use an infinite number of rectangles, we could find the exact area, right? So the more and more rectangles we use, the more accurate our approximation would be. But if we could somehow use an infinite number of rectangles where they're infinitely thin, okay, and we fill up all that space, we could actually find the exact area. All right, so how could I show that I want to find an infinite, right, the sum of an infinite amount of rectangles? And this is how I could do it. I could take the limit as the number of rectangles goes to infinity of my sum that we just talked about, right? So where we have from one rectangle to n, and it's always going to be length times width, where length is going to come from evaluating the function at each x value, and the width is going to be delta x. All right, but we actually learned another way to find exact area. Okay, don't you remember that exact area can be found using a definite integral, right? That's what definite integrals do. They find the exact area. And so remember what I mean when I say definite integral. The integral from a to b of f of x dx. So if I can find, if both of those things will give me exact area, all right, then we can say that the limit as n approaches infinity of this sum is equal to the integral, all right? And since they're equal, then we should be able to convert back and forth between the two. And that's exactly what we're going to do today, okay? We're going to convert back and forth between the two. Now, you do need to keep in mind that for the limit piece, all right, we wrote this on the first page of notes, but just as a refresher so that you have it all together, delta x comes from taking b minus a divided by n, and x sub k comes from taking the beginning of the interval and adding the change in x times k. All right, so those pieces are going to be very important when we actually start working these things out. Okay, so what are we going to do first? Well, the first thing I want us to do is we're going to start with the definite integral, and we're going to write it as the limit of a Riemann sum. Okay? All right, so here we go. I don't want to go quite, I want to be able to see this, at least for the first example here. All right, so first example, I have the integral from 0 to 3 of e to the x dx. All right, so how do I go from integral to limit? Well, I need to figure out what delta x is first, and that's b minus a over n. We don't know n, right? We're trying to find the exact area, so n is going to stay in. Then I need to find x sub k, which tells me I'm going to take the a value, I'm going to add delta x times k, and do any simplifying I possibly can, okay? And then I'm going to plug x sub k into the f of x function. So it's going to become e raised to the 3k over n, okay? Then I am ready. I have everything I need to write my integral as a limit of a Riemann sum, where delta x is 3 over n. So remember, it said it's f of x sub k times delta x, but I can put delta x first if I want, and then multiply by my function, and I'm done. So what I'm saying is this integral is equal to this limit. They would both find me the exact area. Now, if I actually had to calculate the exact area, I would need to do it with the integral, because actually you can't write out an infinite number of terms here and actually add them up. Okay? Now, let's do another one where I'm giving you some similar information. All right? So like, let's do the one from above, from our earlier example. Let's integrate from 1 to 4 of e to the x dx. Okay, now, I'm not actually asking you to integrate. I'm just asking you to turn it in to the limit of a Riemann sum. So just like in the previous example, we need a couple of things. We need to know what is our delta x. We need to figure out what is our x sub k. But remember this time, you have to know the a value, which is not 0 this time, plus delta x times k. I can simplify a smidge by putting the k on top with the 3 if I want. And then I need to make sure that I plug that into my function appropriately. Okay? And then I'm ready to put it all together as a limit of an infinite number of rectangles for the sum of those rectangles, where I have length times width. Width is 3 over n, and length is my function that I've just created. Okay? All right, and let me do it one more time with an e, because I want to show you something. All right, if I go from 1 to 4, but I change it to e to the x minus 1 dx, and I redo everything. All right, I know my delta x is still going to be 3 over n. I know my x sub k is still going to be 1 plus 3 over n times k. But f of x is going to look a little bit different. All right, when I plug in the 1 plus 3k over n for x, I still have to subtract 1 after that, and that simplifies a little bit. Okay, and so then the Riemann sum looks like, the limit of the Riemann sum looks like this. Which actually is identical to the first one we did. And I want to talk about why, okay? So the first one we did would be the area from 0 to 3 of e to the x, all right? The last one we did is the area from 1 to 4 of e to the x minus 1. Well, if you'll remember anything from transformations of graphs, if you subtract and it's grouped with the x, okay, that's actually a right shift, a right one. So what we've done is we've taken e to the x and we've shifted it to the right one and then found the area from 1 to 4. Well, that should be the exact same area as not shifting it, but covering the same amount of space, which would be from 0 to 3. And that's why those two came out exactly the same. And I thought that was a really interesting observation that we can make. All right, now I want to give you 2 more like that just for practice. Just to make sure that we're good if the function changes, since all of those were very similar. All right, so let's say we put a cosine function in here, and all I want you to do is rewrite it as the limit of a Riemann sum, okay? So remember what we need. We need delta x, which is b minus a over n, and we simplify. We need x sub k, which is the a bound plus delta x times k. And then we need to understand what our function is going to look like when we plug that in. And it's going to look like this, cosine of that added piece, okay? And so then we can put that all together, and we can write this as the limit as n approaches infinity of a Riemann sum, okay? And our Riemann sum is our length times width, where our width is delta x, and our length is our function of x. Okay? All right, and then let's do one more right here. All right, how about we go from 1 to e of ln of x dx? Okay, so delta x is going to be b minus a over n. I cannot simplify that in any way, shape, or form. X sub k is going to be the a value, which is 1, plus my delta x times k. Excuse me. I can put k on top, but I would have to put e minus 1 in parentheses. And then f of x sub k would be the natural log of that. I think I'm going to keep these separate this time. Okay? And so then I'm ready to come back up here and put it together. Don't want to run out of room, so I'm not going to write super big. K equals 1 to n. And then again, delta x typically goes in front of the function, but it doesn't have to. All right. And then here is my function. All right. And that is the limit of a Riemann sum. Okay. All right. I know this video is getting long, but I have several things I want to finish, and I don't want to do a second video. So we're going to keep on going. Whoops. I want to move down here. All right, so the next thing I want to look at is I want to go the other way. I want to express the limit of a Riemann sum as a definite integral. Okay, so I have to give you a Riemann sum to start with, excuse me, the limit of a Riemann sum. All right, so let's start with something like this. All right, and when you see it for the first time, you need to think about what are the pieces like that I should be able to pick out, okay? So you should be able, like, remember, this is going to be length times width, where the length comes from plugging something into a function, and the width is usually that, like, that's got to come from your b minus a over n. So your width, your delta x, is the 5 over n, okay? And then it looks like I have plugged 2 plus 5k over n into the function, into the ln function. All right, and so then the x sub k, the part that's got plugged into the function, looks like it's this piece. And if it is that piece, then 2 is a. All right, because this is the delta x times k piece, right? Well, if a is 2, all right, then I should be able to find b, because I know that b minus a should give me 5. Well, if a is 2, then b should be 7, okay? All right, and now we're ready. We know that we have to integrate from 2 to 7. So x sub k was plugged into the ln function, all right? So instead of writing ln of x sub k, we just write ln of x. And then instead of writing delta x, we write dx, and we're done. Okay, now there actually is another way to do this problem. All right, there is another way to do this problem. All right, so I want to show you. Okay, if you just decide that all of the integrals start at 0, a is 0, then b would be 5, so that b minus a is still 5, right? But if I say that, then when I think about the formula for x sub k, where it's a plus delta x times k, okay, then x sub k is just the 5k over n, right? This would just be my x sub k, which means the 2 was already part of the function, okay? And so then my integral would look slightly different. I would go from 0 to 5, but the 2 would already have been part of the original function, and the x sub k was just the 5k over n, so that's where my x goes. Okay, I prefer reading it like this when there's already a number added to something else, but both of these would give you the identical area if you were to work them out. Okay, they would give you the exact same area if you were to work them out. All right. Give you another one. All right, so when you first look at this, you really need to just figure out what are your pieces. All right, so from what I can tell, delta x is going to be the 4 over n. All right, again, so then I look for the 4 over n times k, all right, and that's in parentheses with a plus 2. So I'm going to say all of that is my x sub k, which means a is 2. Well, if a is 2, then, and b minus a is 4, b has to be 6, okay? And that's really all I need to write my integral. I know I have to go from 2 to 6. The 1/5 is part of the function. 2 plus 4k over n, that's my x sub k, so that becomes my x, and then it's squared. And the 4 over n is my delta x, and that becomes my dx, and I'm done. Again, you are welcome to start at a equals 0, right? But your integral will look different, okay? Or if a equals 0, then b equals 4, okay? And if I do that, then I have not accounted for the 2. And so the 4k over n is my x, not the 2 plus 4k over n. And so then it looks like this. All right. Now, you got to think about it. If you were to actually have to find the exact area, which one would be easier to integrate? The one that has a 2 plus x in parentheses, or the one that just has an x in parentheses? I think it would be easier to integrate this one. Neither one of them are very difficult, but I personally think this one would be easier. Okay. All right. And then one last part here. And I'm actually going to pause the video real quick while I write it down. Okay, so what I'm asking you to do here is I'm still asking you to express the limit as a definite integral, all right, but then we're actually going to calculate the integral. And I've written the limit a little bit differently. I've actually shown you the pieces of the sum, and you have to figure out like what was the formula and all that stuff, okay? So you can definitely tell that that 3 over n has been factored out. So that is my delta x, all right? And if you look at the very last term, it kind of helps you see what the pattern is better, because when they plug in this last n, right, that's really where the k would have been in each individual term, all right? And so you can see that like the formula for x sub k can be written as 2 plus 3k over n. And then you can just kind of see like if the first, remember k is the rectangle, so the first rectangle would make this 3 over n. The second rectangle, if k is 2, that's how I got a 6. When k is 3, that's how I got a 9. All right, and then at the very end, when k is n, that's how I get the last one. All right, and so then we can see that if that's x sub k, then a was probably 2. If b minus a is 3, then b is 5. All right, and so my integral is going to go from 2 to 5. All right, now look, each time x sub k is raised to the 4th. So then x is raised to the 4th for my function, and that is something that I can certainly integrate pretty easily by hand, right? You use the power rule, and then you plug in the bounds. 5 to the 5th is 3125. 2 to the 5th is 32. And when I put all that together, I get 3093 times 1/5 is 3093 over 5. Okay, I'm not even worried about trying to simplify that anymore. All right, I've got one more like this for us, but again, I'm going to pause while I actually write it. All right, so this one looks a little bit more complicated, but it really isn't in terms of the amount of work. You still need to figure out what is delta x. If you look at the last term, you can kind of figure out what the pattern is, and then you can look back to make sure that you can confirm it. But when I have 2n over n, it's not reduced on purpose, because this last n is really what k was filled in for each time. All right, so x sub k must have been 2k over n squared plus 6 times 2k over n. And notice that that doesn't have a constant added to it. So we are going to assume that a is 0. And if a is 0 and delta x is 2 over n, then b minus a is 2, b must be 2. Okay, so we're going to integrate from 0 to 2. All right, and if x sub k wait, I did that wrong. Oh, okay. So give me a second. I wouldn't really call this x sub k. This is the function when x sub k has been plugged into it. Okay, so that's, each piece looks like that. So that's the function. Did I do that right up here? Hold on. Well, I didn't actually write it out up here because each one of these is the function. All right, so I didn't write that the same way up there. All right, so then that means x sub k is just the 2k over n, right? That's the piece that's been plugged in. So the function, if this little piece is x sub k, then the function is x squared plus 6x. All right, and there's my definite integral, and if I wanted to find the answer to that, then I would have to use some power rules, do some simplifying, and then plug in my bounds. Okay, and you guys should be able to plug in those bounds, and I will tell you the answer should come out to be negative 73 over 3. Okay, and that is several different ways to see this topic asked. I have put 2 practice worksheets in the Canvas module. One of them is a practice assessment, so you should definitely practice, because that means we're going to have an assessment next time after we go over the homework.